Hi, today's lesson is going to be on conservation of energy. But before we get into that, let's review really quick another conservation law that we learned, conservation of momentum. In the last unit, we learned that conservation of momentum means that the momentum in a system before an event is equal to the momentum after that event in that system. And it was symbolized by Pi equals Pf. Okay? And from this equation, we would build out these big complicated equations that showed the momentum and the mass and the velocity of each individual object in some sort of collision or explosion or event in general, etc. There's a rule for telling when you could use conservation of momentum. It only occurred in situations when the net force on the system was 0 newtons. And that actually made sense because if the net force was 0, the definition of impulse was net force times time. And so if the net force is 0, the impulse was 0. And another way to think about impulse was that it was equal to the change in momentum. So if the net force is 0 newtons, the impulse was 0 newton seconds, and therefore the change in momentum was 0. In other words, the total momentum stayed the same. Conservation of energy is a very similar idea. It refers to the idea that the total energy of a system before an event is equal to the total energy after an event. And again, event just means something happens. The equation for conservation of energy is kind of weird. It's the exact same thing kind of written twice. ET equals ET. And this is, as a matter of fact, this is up in my room above my board. ET equals ET. It looks really weird, like obviously something is equal to itself. But trust me, ET equals ET is going to be a good way to start a lot of your written work for these questions. So, when is the total energy of a system conserved? Okay, total energy is ET. It is conserved when no net work is done on a system. We know that work is the change in energy for some system. So if you don't want to change the energy, no work can be done. In other words, no outside force does work. Remember that work is done by forces. So if no outside force does work, then the total energy can't change, and therefore it's conserved. The outside forces that we're talking about, like we mentioned in the last video, are the applied force, tension, and the normal force. All of these forces go into changing the kinetic energy of an object specifically, just the kinetic energy. The other forces that we talk about, the force of gravity, force of friction, spring force, those can change the kinetic energy, but they can also change those other types of energy, such as gravitational potential energy, elastic potential energy, or internal energy. Therefore, when we write out a conservation of energy equation, if those forces are doing work, they're included because we're specifically keeping track of the types of energy that they change. Similar to when we did this for momentum, we're going to write out our steps for solving problems involving work and energy. The very first thing you do is you determine if work was done, and I'm going to put in parentheses, by those three forces we listed above, the applied force, the tension, or the normal force. There's only going to be two options. Either work is done by those forces, or it's not done by those forces. So, if work is done by those forces, at least one of those forces, you're going to do what we did in the last video. Determine what types of energy changed, and then you simply use the equation, the work done is equal to the change in total energy. It's exactly what we did in the last video. It's pretty straightforward. However, if those three forces are not present or none of them do work, you're going to have something a little bit more complicated. Not complicated, I should say, but just different steps. If no, what I would like you to do is draw a picture. You're going to pick 2 points in that picture that are relevant to what's happening in the problem, and you're going to label them I and F. And why you're doing that is going to be clear, is going to get more clear as we go. Once you do that, you're going to use the equation ET equals ET. Because again, if no work is done, then the total energy stays the same. This is the side for I, this is the side for F. If you haven't figured out by now, I and F stand for initial and final. You can think of the left-hand side of this equation as the initial side, the right-hand side is the final side. You're going to determine the types of energy present at I and F. You're going to set the types of energy equal in the ET equals ET equation, and then you're going to solve for whatever you're asked to solve for. This process will make more sense as we go. And by the way, I'm just going to tell you right now, all of these examples that we're about to do involve this. We already did all the examples that have work being done by an outside force and the total energy changing. Today, we're going to focus on situations in which energy is conserved, therefore ET equals ET. First example, a 40-kilogram boy jumps off a diving board 3 meters above the surface of a pool. How much kinetic energy does the boy have just before entering the pool, and how fast is he moving? So here's our boy on a diving board. Okay, he has a mass of 40 kilograms. It says jump, but we're just going to say, let's just say he falls off into the water, and that is a distance of 3 meters. Okay. Our first step in determining if we should use conservation of energy or the work energy theorem, conservation of energy, is to figure out if work is done by any of these three forces, the applied force, tension, or normal. There's no person or animal pushing him, so the applied force is out. There's none of that. There's no tension. There's no ropes attached to him. You could argue that there is a normal force when he's on the diving platform or diving board, but if he just kind of falls off, there's no normal force on him during his fall. Okay, and that's not really changing the energy. So there's no normal force on him during his fall. So we're going to conclude that no work is done by an outside force in this case. As a matter of fact, you might even say that boy is in free fall. And that's a very special case because objects in free fall conserve energy. Okay, the total energy doesn't change for an object for a system in which an object is in free fall. You're going to move down to your next step because now we know that no work is done by an outside force. So we know we're going to use ET equals ET. Your next step is to pick 2 points, label them initial and final. Well, it's kind of obvious. The initial spot is where the boy is up on the diving board. The final spot is right before he hits the water. Okay? So you can write I and F over here, I here, F over here. You could even write like diving board and water here. I get people who get a little confused with ET equals ET. I think it's enough if you remember that this is the initial side, this is the final side. All right. Now you determine the types of energy present at the initial spot and the final spot. This shouldn't say and, it should say at. So let's look initially. The boy is just about to leave the diving board. What types of energy does he have? Well, if he's just about to leave, he doesn't have kinetic energy yet. He's on a diving board or diving platform, and I guess you could make an argument there's some spring energy, but let's assume that he's not bending the board at all. He's really, really light. So there's no elastic potential energy, and there's no internal energy, okay? There's no friction acting on him. The only type of energy he has is gravitational potential energy. So if he's only got gravitational potential energy, I'm going to write that on my initial side. He's got initial gravitational potential energy. At the end, what type of energy does he have? He no longer has that gravitational potential energy because he's now at the water's surface. He's fallen down. There's still no springs. There's still no friction acting on him. Now he must have kinetic energy because he's moving. He's moving very fast right before he hits the water. So we write KEF. In other words, the initial gravitational potential energy that he has is equal to the final kinetic energy that he has. Energy was conserved. All the energy started off as elastic potential or as gravitational potential energy. It converted to kinetic energy. The first question is, how much kinetic energy does the boy have? So we're solving for KEF. I know that the gravitational potential energy equation is mgh. I'm going to put an I there because we're talking about initial. The boy's mass is 40 kilograms. The acceleration due to gravity is 9.81 meters per second squared, and he's falling from a height of 3 meters. If I calculate all that, I should be able to find the kinetic energy right before he hits the pool surface. He has 1,177.2 joules of kinetic energy right before he hits the surface. And if you think about it, because we know the final kinetic energy is equal to the initial gravitational potential energy, that's also how much gravitational potential energy he had before he fell. We're also asked to find how fast he's moving. Since we know the kinetic energy, that's very easy. 1/2 mv squared, 1177.2 joules, equals 1/2 40 kilograms Vf squared. We solve for Vf, and we get 7.67 meters per second. That's how fast the boy is moving right before he enters the water. Now, if you're saying we could have done all of that with one kinematics equation, at least finding the speed, you're absolutely right, and you would get the exact same answer. This is a case where you can do that, and you can use just kinematics to find the answer. Some people might prefer energy, some people might prefer kinematics. It doesn't really matter. The next question is a case where we're not going to be able to use kinematics, and we have to use energy, and I'll explain why. A 72 kilogram skateboarder at the top of a half pipe drops in and rides his skateboard to the bottom. If the top of the half pipe is 6 meters tall and there is negligible energy loss due to friction, how fast is the skateboarder moving at the bottom? Here's what that half pipe looks like, more or less. Here's the skateboarder. Okay? And they're going to move like this. And it's 6 meters from top to bottom. Our first question, again, is determine if work was done by the 3 forces above. There's no applied force, nothing is pushing him. There's no tension, no ropes. There is a normal force this time. You might argue there's definitely a normal force. Normal force is always perpendicular to the surface the object is on. Our object is a skateboarder. The ramp of the half pipe is right here. So you might say there is a normal force. It's pointing to the right now. And as the skateboarder goes down the ramp, it's going to start to point up because it's always perpendicular to that surface. Now that's true. You're absolutely right that there is a normal force. However, for the normal force to do work, for any force to do work, it must be directed in the direction of the motion of the object. This skateboarder is moving down right now when he's at the top. The normal force is directed to the right. That's a 90-degree angle between them. And remember the work equation. Work equals force times displacement times cosine of theta. If the angle between the force and the displacement is 90 degrees, and you take the cosine of that, that's 0. So the fact that the normal force is there still doesn't matter because it's perpendicular to the direction of motion. Matter of fact, that's true all throughout the motion. The skateboarder, as he moves down, always has a normal force on him, but it's always perpendicular to the direction of motion. Therefore, the normal force does no work. None of the other forces do any work on him, the outside forces. Therefore, no work is done, and we can start with ET equals ET. This is a situation where energy is conserved. The initial spot that the skateboarder is at is up here. The final spot is down here. We're looking to see what types of energy he has at initial and final. Initially, the skateboarder hasn't started to move yet. There are no springs or anything that the skateboarder is attached to, and there's no friction. We're saying negligible energy loss due to friction, so we can conclude that the only type of energy the skateboarder has up here is, once again, gravitational potential energy. At the bottom, he lost that gravitational potential energy, but because energy is conserved, it had to go somewhere. Still no springs, still no friction. It must now be kinetic energy. So we actually have a situation that is similar to up above, but you'll see that there's definitely something different here. We want to know how fast the skateboarder is moving at the bottom. I'm going to write out my equations for gravitational potential energy and kinetic energy. Gravitational potential energy is mghi. Kinetic energy is 1/2 mvf squared. Notice that both of my equations have an m in them. That means I could divide both sides by m and get rid of them. The skateboarder's mass actually doesn't even matter. That 72 kilograms is extra information. So now I'm going to plug in and solve. G, acceleration due to gravity, is 9.81 meters per second squared. The initial height is 6 meters, equals 1/2 times the final velocity squared. That's what we're looking for. 9.81 times 6 divided by a half, take the square root. At the bottom, the skateboarder is moving 10.85 meters per second. That's pretty fast. Now, interestingly, you cannot solve this question, or it would be very, very hard to solve this question using kinematics and forces. Reason being, that skateboarder does not have a constant acceleration. He's not in free fall. There's a normal force acting on him the entire time. So because you're not in free fall, the acceleration is not just the acceleration due to gravity. It's actually constantly changing from almost free fall up here to basically zero down at the bottom. You can't use kinematics equations and forces when the acceleration changes. Or I guess you could, but you would have to use an infinite number of free body diagrams to show that the skateboarder is moving down this ramp where there's different accelerations an infinite number of times. No one has time for that. Instead, in situations where the acceleration is changing, okay, you could think of it as the net force changing, you can think of it as the acceleration changing, but regardless, in those situations, you want to use conservation of energy, or you want to use energy principles in general. You can't use kinematics for this. Okay? You can't get a solution by using kinematics equations. You have to use the concept of conservation of energy. And you'll see that happen at least a couple more times as we go through these examples. Our next example says that we have a 3 kilogram box moving to the right at 5 meters per second on a horizontal frictionless surface, and it's brought to rest by a spring. If the spring constant of the spring is 500 newtons per meter, how far must the spring compress in order to stop the box? Okay, so there's our spring. Here's our box, and it's moving towards the spring. Eventually, the box is going to hit the spring, and the spring is going to start to push on the box. The spring is going to get compressed, therefore it's going to start to push on the box to the left. It's going to slow the box down, and eventually you'll make it come to a stop. We want to figure out if this is a case where work is being done and total energy changes, or if energy is conserved. So, is the applied force acting on this box anywhere? No. Is there tension? Is there a string? No. Is there a normal force? Yes. But again, the box is moving to the right, the normal force is directed up, they're at right angles to each other, therefore the normal force does no work. That means we can use ET equals ET. If we start with ET equals ET, before the box has hit the spring, that's the initial spot. Once the box has compressed, or once the box has compressed the spring as far as it can go and has been brought to rest, that's the final spot. Initially, well, let's just take care of this right now. There's no change in height anywhere here, okay? So there's no gravitational potential energy we have to worry about. It also says that this is a frictionless surface, so there's no friction we have to worry about. Initially, the box is moving and the spring isn't compressed, so there's only kinetic energy. At the end, when the spring is fully compressed, it's not moving, so there's no kinetic energy, there's only elastic potential energy. All the kinetic energy from the box before it hits a spring got converted into elastic potential energy. If you were to allow that spring to push back out, all the energy would turn back into kinetic energy. I can find the amount that the spring has to compress by writing out the equations for both these terms. Kinetic energy is 1/2 mv squared. Elastic potential energy is 1/2 kx squared. I'm just putting initial and final to note what's changing. You'll notice I have a 1/2 in both terms of the equation. That means I can divide out the 1/2, cancel those out, and I can plug in. The mass of the box is 3 kilograms. It's moving to the right at 5 meters per second. Got to square that. The spring constant is 500 newtons per meter. And x, the final amount of compression, remember that's what x is, compression or stretching, is what I'm looking for. So 5 squared times 3 is 75. Divide by 500, and then take the square root. I get that the amount that the box has to compress is 0.39 meters. That amount of compression will allow it to store all of the kinetic energy. And if all the kinetic energy is now elastic potential energy, the box has stopped moving. That's the farthest that the spring is going to compress. My next example, you're going to see a lot of roller coaster questions in this little unit. Roller coaster cart is at rest at the top of the first hill in the track at a height of 60 meters. It descends the first hill, climbs up the second hill to a height of 45 meters. If the track is frictionless, how fast is the cart moving at the top of the second hill? So we've got something that looks kind of like this. This is a 60-meter hill. Here's a roller coaster at the top. Here's the 45-meter hill. Okay? The roller coaster is going to go all the way down and then back up. It'll end up here. There is no applied force anywhere. Nothing is pushing the roller coaster. There is no tension. There's no strings involved or ropes. And there is a normal force, but just like with our half-pipe example, the normal force is always perpendicular to the direction of motion for the cart. So no force does any work. No outside force does any work. Therefore, energy must be conserved. This is our initial spot. This is our final spot. Initially, we know that the roller coaster is at rest, so no kinetic energy. And again, no springs are here, no friction because it's frictionless. The only type of energy that is present is a gravitational potential energy. At the end, it's clearly got less gravitational potential energy because it's not up as high. It's got some, but it's not up as high. So PEGF, there's still no springs involved. There's still no friction involved, so no internal energy or elastic potential energy. But if it's got less gravitational potential energy, what happens to the rest of the energy? Well, think about it. The cart went down, it comes up, it's probably got some speed up here. It's probably got some speed, and so therefore it's probably got some kinetic energy. Getting to this step is almost as important as continuing on and solving the entire question and doing the entire question. If you can get here, then the rest of this is just math, understanding what types of energy are present at each spot. So we're going to write out the equations for each of these terms. This will be mghi equals, on the other side, mghf plus 1/2 mvf squared. There's an m in every single term. That means I can divide everything by m. They will cancel out. I can't divide g out because this term does not have a g in it, unfortunately. So I'm left with 9.81 meters per second squared times 60 meters equals 9.81 meters per second squared times 45 meters plus 1/2 VF squared. I solve this for VF, 9.81 times 60, subtract, in parentheses, 9.81 times 45. Okay, that's a difference in potential energies, which means if that's the difference in potential energies, that's got to be how much kinetic energy there is. But I want to solve for the speed. I now divide by 1/2, and I take the square root. I get that the final speed of the cart is 17.16 meters per second at the top of that hill. Like I said, you're going to see roller coaster questions a lot. This example is intended to show you that you can have more than one type of energy at once. Sometimes people think you can't have more than one type of energy. You can have as many types of energy as there are. Okay? You could have something that is moving up a hill, so it's kinetic energy, it's got gravitational potential energy, it's compressing a spring as it moves up a hill, and there's friction involved. You can have something have every single type of energy if you want. Last two examples. You have a 1.5 kilogram cart that you place on top of a ramp that starts 0.6 meters above the ground. How much potential energy does the cart have on top of the ramp? We're talking about gravitational potential energy. This is pretty straightforward. PEG equals mgh. PEG equals 1.5 kilograms times 9.81 meters per second squared times a height of 0.6 meters. .5 times 9.81 times 0.6. The gravitational potential energy is therefore 8.829 joules. That's how much energy is stored in the system thanks to it being up above the ground. B says, assuming no friction, when the car gets to the bottom of the ramp, how much kinetic energy does it have and how fast is it moving? So we've got this ramp here, 0.6 meter ramp. Here's where the object starts. It gets down to the end. As usual, we check. There's no applied force here. There should be a straight ramp, by the way. I think I drew it with a little bit of a curve. There's no applied force here. There's no tension. There is a normal force, but it is always perpendicular to the direction the object moves, so it does no work. We know that energy is conserved. Up here at the top, it hasn't started to move yet. There's no springs involved. There's no friction. This is frictionless, it says. So it's only got a gravitational potential energy. At the bottom, it no longer has that gravitational potential energy. No elastic, no internal. It's only got kinetic energy. Hopefully you're seeing a theme that kind of repeats itself over and over. The initial gravitational potential energy was the gravitational potential energy that it had up here. Here's I, here's F. We already found that. 8.829 joules. That's how much kinetic energy it has at the bottom. How fast is it moving? That's pretty simple. KEF equals 1/2 mvf squared. The kinetic energy at the bottom is equal to the potential energy at the top. 8.829 joules equals 1/2 times 1.5 kilograms vf squared. The final velocity is 3.43 meters per second. That's the final velocity if there's no friction to worry about. What if, during the cart's descent, its internal energy increases by 5 joules? That's friction. That's not an outside force, so we can still say that energy is conserved, but something else is coming into play here. Now we have to account not only for the initial gravitational potential energy and the kinetic energy at the bottom, because it's still going to reach the bottom, we also have to account for internal energy. Notice that we didn't change the gravitational potential energy initially. That means that by including 5 joules of internal energy, we're going to be decreasing the kinetic energy. That's the only way to have these two still add up to the original amount of gravitational potential energy that was present initially, is if the Q increases, because we're adding in some internal energy, we're saying that now there is friction on the track, the kinetic energy goes down. So this should decrease the kinetic energy. We already know the gravitational potential energy initially, but I'm going to write out 1/2 mvf squared plus q. So now we can plug in all my numbers. 8.829 joules equals 1/2 1.5 kilograms vf squared plus q, and q is 5 joules. So notice I've got to subtract the 5 over to the other side first. That leaves me with only, for the kinetic energy on this side, 3.829 joules. So just like we said, the kinetic energy goes down. 1/2 1.5 kilograms equals, let's see, we subtracted 5 to the other side, so that's 3.829. I guess you didn't have to do all this math, but I did anyways. So 3.829 divided by half, divided by 0.5, take the square root. Now, with friction involved, the car only moves at the bottom 2.26 meters per second. So not only, we could have predicted that before, friction slows things down, but now we also see that it takes energy, it takes kinetic energy away from a system, changes it to internal energy. So that's kind of interesting that we're just getting another look at it. Last question. An 87 kilogram skier at the top of a hill that is 30 meters tall skis down to the bottom. At the bottom, his speed is 16 meters per second. How much mechanical energy has been lost due to friction? Anytime you see that, it means find Q. If you see how much mechanical energy has been lost due to friction, it means there is friction present. So you need to find how much energy has been taken by friction. In other words, how much internal energy has been generated. Here's our skier. Top of a 30-meter hill. Here's where he starts. Here's where he ends up. Again, no applied force, no tension. Normal force does no work because it's always perpendicular to the direction of motion. We start with ET equals ET. The skier has gravitational potential energy up here. Not moving yet. No springs, no friction at the top. By the time he gets to the bottom, he doesn't have that gravitational potential energy anymore, but he does have some kinetic energy. And since we're looking for how much energy is lost due to friction, we add plus Q. We're assuming that there must be some internal energy that was generated. Again, if you can get to this step, the rest of it is just math and it's pretty straightforward. mghi equals 1/2 mvf squared plus Q. Another way to tell that there must be friction acting on this and there must be internal energy being generated, take a look at what we're going to get when we calculate the initial gravitational potential energy and the final kinetic energy. I can't cancel out mass because mass isn't included here with Q. 87 kilograms times 9.81 meters per second squared times an initial height of 30 meters. 87 times 9.81 times 30. That's how much energy, I'm going to write this up here, that's how much initial potential, gravitational potential energy there is. What about the initial, or what about the final kinetic energy? Skier's mass is 87 kilograms. His speed at the bottom is 16 meters per second. You're just being told that this time. If I do 16 squared times 87 times half, look at how much kinetic energy there is at the bottom. Only about 11,000 and a little bit joules. Where did the rest of it go? It must be internal energy. The fact that there was friction converted a lot of that kinetic energy that would be there if there was no friction into internal energy. So now it's relatively straightforward to find Q. 25604.1 minus 11136. The amount of internal energy is 14,468.1 joules. So there's a real quick rundown of a whole bunch of examples of conservation of energy. This is one of the tougher parts of this unit and actually the whole year. Conservation of energy can be a little tricky because there's tons of different situations you can look at. But if you follow the steps, determine if this is a situation where you can say energy is conserved, and then pick an initial and final spot, write out the types of energy. If you can get to this step right here, all the rest of this is just writing out equations that you already know and doing some math, okay? And every one of you can do that. We've got 2 little mini topics left, and then we'll move on from our energy unit. Talk to you later.